Hello everyone, welcome to this channel. So in this video, we will continue our topics of probability. So in this video, I want to talk about what is a standard normal distribution. So in last video, we already introduced the normal distribution. So that means random variables have a specific form of its PDE, the probability density function. Then this random variable is a normal distribution. So for this standard normal distribution was this definition. So if we have first a normal random variable and we have the expect value or mean of this random variable is equal 0 and the variance of this random variable is equal 1. So in this situation, this random variable is a standard normal random variable. And to differentiate between a normal random variable with a standard normal random variable, in general, we use the capital Z to denote the standard normal random variable. So here in this one, the symbol to say a random variable is a standard normal random variable is like this. So this is n parentheses 0, 1 parentheses. And also for the cumulative distribution function of a standard normal random variable, what we will use a Greek letter, this capital phi, to denote it the value of this CDF, cumulative distribution function, at value small z. Okay, so here, of course, if you look at my video for the normal random variable, I already said the CDF is actually defined as integral from negative infinity to x, like the CDF is equal negative infinity to x of our PDF with respect to the du, right? This is definition of our CDF. However, because the PDF of a normal random variable is not integrable, it's not easy to get an explicit equation of the CDF. So what we will do here in general, we can have a table of the standard normal random variable. So that means for this table, they will give us if we have a specific value of our small z, then in this table, this will tell us how to find the answer of this CDF. So in other words, how to find the probability when we standard normal random variable z is smaller or equal to this specific value. Okay, and so because for the statistics and also probabilities, it's really easy for you to find a table for the standard normal random variable. So what people will do when they try to find a probability of a normal random variable, so the way they will do is they will rewrite this normal random variable to a standard normal random variable. So the way to write this is look like this. So here assume we have a normal random variable, and this random variable has a mean is denoted by mu, and the variance is denoted by sigma square. Then we can define another random variable. So here we denote this by capital Z. So this capital Z is defined as x minus mu divided by sigma. So that means this use our original normal random variable minus its mean and divided by its standard deviation. So here actually we skip all the proof of why this, but by this definition, the new random variable capital Z is a standard normal random variable. And also the relationship between these two random variables, this equation here, give us the relationship between the the CDF, or in other words, the the probability of our random variable smaller or equal to a specific value. So if we try to find the probability of our original random variable x smaller or equal to a small x, then this is equal our probability of our new random variable capital Z smaller or equal to a small z. So here this small z is defined by the value of our small x minus the mean mu divided by the standard deviation sigma. So this is how we can use our equation capital Z equal capital X minus mu divided by sigma to rewrite a normal random variable to a standard normal random variable. And also, as we said previous, because the value of phi is given by a table, so you can easy to find this table in any website. Just Google it, and then use this table, we can get the value of our phi at small z, and this will give us our answer how to get the probability of our x random variable small or equal to small x. Okay, so now let me quickly give you one example of how we can use this method to compute the probability of a normal random variable. So now let's look at this example. So now we have a random variable x, and by this symbol we know x is a normal random variable with a mean is equal 5.75, and this sigma square is equal 0.1225. So the question is ask us what is the probability when our x is greater or equal to 6.7. Okay, so to compute this, what we should do is the first thing we know, because our random variable is a normal random variable, so we want to rewrite this as a standard normal random variable. And the second thing is then we want to use the table of our standard normal random variable to compute this probability. However, if you compare this one with our definition of the CDF, so for our CDF, this is always equal like CDF as Z, or maybe we use the CDF P fx. So this is always equal capital X smaller or equal to a small x. So that means instead of the question x greater or equal to 6.7, what we want some symbol like smaller or equal to. So that's why the first step, instead of rewrite this normal random variable to a standard normal random variable, what we should do is we should first rewrite our probability to a smaller or equal to equation. So that's here by the axiom of our probability. What we have this actually is equal 1 minus x smaller than 6.7. Okay, so this is just because the probability of the all possible values, x equal all possible values, should always equal 1. And then by this random variable, we know this is a continuous random variable. So in previous, when we talk about the continuous random variable, we already said the probability of our continuous random variable equal a specific value is always equal 0. So that means here for this x smaller than 6.7 is equal to the value of x smaller or equal to 6.7. Because here the equal part is just this probability will equal 0. So now when we have this equation, the next thing is we want to rewrite our random variable to a new standard normal random variable. So that means for the both sides of this smaller or equal to symbol, we should minus our mean and divide it by the sigma. And then what we should do is we should plug in the value of our mean and sigma. And then the left hand side of this smaller or equal to symbol is our new random variable, and this is a standard normal random variable. And the right hand side we need to plug in the value. So here the mean is equal 5.75, and then for the denominator, this, please remember, this is a sigma, not sigma square. So that means this, what we want in the denominator is a standard deviation. It should equal the square root of our sigma square, or in other words, the square root of our variance. So if you use your calculator to compute the square root of 0.1225, you will find the value of this is equal 0.35. Okay, so now what we have this actually is our CDF of a standard normal random variable at value, so 6.7 divided by minus 5.75 divided by 0.35. This is equal x smaller or equal to 2.71. Okay, so in other words, this is our CDF of standard normal random variable at 2.71. So then you can just look standard normal random variables CDF table. We will find the value of this CDF is equal 0.9966636. So that means the answer of this question will equal 0.003364. Okay, so this is how we can compute an example of this question. And in this one, this is an example of this. And then before the end of this video, I want to just a summary about the step we do here. So that means we rewrite the probability of x greater or equal to a value to 1 minus the probability when this x is smaller or equal to another value. So let me write this as a remark. So this is by the axiom of the probability. However, for our normal random variable, we have one more property of this. So we know for a normal random variable, this actually is a bell-shaped function. So what this means? This means this will be symmetric with respect to the value of its mean. And for the standard normal random variable, what's the special of this? The special thing is the mean of this standard normal random variable is equal to 0. So in other words, the graph of the PDF of standard normal random variable is symmetric with respect to our y-axis. So that means here is a vertical axis. So based on this, what we will have one more special remark here. So when this is about a CDF for our standard normal random variable. By the definition of a CDF, we have this first line. The CDF of our standard random variable should at value A should, by the definition, is the probability of our capital Z smaller or equal to A. And then similar with the previous remark, this means we will have this function, this probability is equal 1 minus probability Z greater or equal to A. This is by the axiom of the probability. And then by this one, actually what we will have by the symmetric of this graph of our PDF, what we have, the probability Z is greater than A actually is the shadow part on our graph. So this is the probability of the area of this shadow part is the probability of our random variable capital Z is greater or equal to A. And by the symmetric of our graph, what we have this actually is equal the shadowed color, the red shadow part. So here, by the symmetric property of this graph, we know the value of this is actually the probability our capital Z is smaller or equal to negative A. Okay, so this is a one important equation and how we can get the third equation. And also by the axiom of probability, we know this actually is equal to the probability capital Z is greater or equal to negative A. Okay, so this is what I want to talk about, the remark here. This is a really important properties for this CDF of a standard normal random variable. This is based on the special symmetric property of the graph. Okay, so this is the end of this videos, and hopefully you like it, and please subscribe this channel. In next videos, I will start to talk about the relationship between two distributions. One is a discrete random variable and the other is a continuous random variable.